right, everyone. I am here with Julieta Martinez. Julieta is a senior research scientist at Waabi. Julieta, welcome to the TWiML AI podcast.
Thank you. Thanks for having me.
I am really looking forward to diving into our conversation. We're going to talk all about some of your research into computer vision. To get us started, why don't you share a little bit about your background and how you came to work in the field?
Yeah, of course. So I started, so I was born and raised in Mexico. And around 2011, 2012, I finished my undergrad there. And I really wanted to go somewhere else for grad school. So I applied to a bunch of universities in Canada. Then I got accepted into the UBC, the University of British Columbia. And then I started doing my master's there. Then eventually went on to do a PhD with the same institution, same supervisors. And then in 2018, I was wrapping my PhD, but like I just had to defend. So I started looking for jobs, and I ended up moving to Toronto to Uber ATG, which was this lab that had just been founded in self-driving. Then earlier this year, that lab shut down, and a few weeks later, a little bit later after that, I joined Waabi, which is where I'm working at right now.
Awesome. Tell us a little bit about Waabi. What is Waabi doing?
So Waabi is a company dedicated to build the next generation of self-driving. And so what we believe is that self-driving is the most important and exciting technological innovation that we will see in the next few years. And Waabi's deal is trying to build upon the lessons of the last 20 years and try to build an approach that is AI first. So not just something that is hand engineered and where then we try to put AI to make it better, but something that right from the get-go can really put AI in the center stage.
Awesome. And so when you say kind of AI first versus bolt-on AI after, what are the implications of that approach? Where do you see it express itself? I imagine that everybody says that, but it means different things.
So I guess it means that when you're building a system, you really have this choice of going for a more traditional approach and then trying to alter some parts of the stack with learned parts, I would say. But if you want to, it actually takes a lot of engineering effort and there's a lot of overhead in trying to do this replication on a system that is in production. But if you build a system that from the start takes this into consideration, then it should be easier to say, for example, experiment on which parts should be learned or which parts should not, or which parts should be trained end-to-end and which parts should be trained separately. There are all these questions that arise when you are trying to decide what the role of AI should be. And so I think it's really something that we're trying to do from the very start, if that makes sense.
Got it. Yep. And so you actually this week, as we're recording this, are presenting at CVPR. You've got a couple of papers at the conference that we'll talk about, and you're also doing a keynote talk at the Latinx AI Workshop. Let's start there. Tell us about the talk that you're doing at the workshop.
Right. So first of all, I would want to thank the organizers of the workshop for inviting me. It's funny, there's not a lot of people from Latin America in the field, say ML and computer vision in particular. So there's a couple of us, like maybe 5 of us, 6 of us, that we have been trying to meet up every time there's a conference. We started with hanging out at the conference. Like sometimes someone will come to your poster and be like, you notice that maybe there are like Latin Americans, you will be like, hey, do you speak Spanish, and so on. And then we would start like saying, hanging out, like going for lunch or trying to build a little bit of a community amongst ourselves.
Mm-hmm.
And then this Latinx in AI organization started. I think it was at NeurIPS where it started.
Mm-hmm.
And so then it started branching out to other conferences, and now there's a more formal presence, I would say, and more and there's a workshop where like submissions from people from Latin America are encouraged, and where we want to also highlight to have speakers from Latin America or Latinx living in the US or in Canada or in other parts of the world. So I think this is the first or second time that we are doing this official thing with official sponsors and official keynotes and posters and so on.
Okay.
Right. So that's how that happened.
Got it. And the presentation that your talk, what's the title of your talk?
So I decided to name my talk, what does large-scale visual search and neural network compression have in common? Because I think the answer to that shouldn't be obvious, and I think they would encourage people to come to the talk.
So let's dig into that. What do large-scale visual search and neural network compression have in common?
So the argument that I tried to make there is that so first off, the motivation is that we know that there's large neural networks that are currently are achieving state-of-the-art performance on all sorts of tasks in computer vision, natural language processing, and so on. And so they're the big elephant in the room. In particular, there is evidence, and I think this started in the NLP side, but now there's some papers that are showing this for computer vision tasks too, that the performance of these models scales log linearly with how many parameters they have, which eventually requires more compute and requires more data. So we are at a moment where we have kind of known for a couple of years that this was going to happen, but now we have like very, very clear evidence, very clear empirical evidence that larger models are something that we're going to need. Mm-hmm. And so this means that we now have models that have billions of parameters, and models that have trillions of parameters are coming. Mm-hmm. And so this means that if you want to deploy these models into a system, you have to compress them. Like there is no going around that. Unless you have you are in a very high-end lab where you have access to a supercomputer, even if you're trying to, even if you have a powerful desktop or a powerful laptop or a powerful server, for these models that have billions and billions of parameters, you're going to have to compress them anyway. So that is, it sounds like it's a new problem that we are facing, and it is kind of new in the context of neural networks. At no point in history have we ever built these trainable systems that are so large.
Right.
But it's also true that we have seen similar problems in other areas. And we had similar problems before deep learning took center stage in the computer vision community. So in particular, myself, when I was doing my PhD, I worked on this problem called, it's called a large-scale approximate nearest neighbor search.
Okay.
And so this problem arises when, say, for example, you have a database of images, and you want to find objects in them. So you want to match something in them. So the way you do this and the pipelines we had would be, say, from a 1080p image, you would run this through a key point detector, and then you would find a bunch of features. And a fairly high resolution image, but not super high, like say 720p, 1080p, it would give you around 10,000 descriptors. And so then when an image comes, you have to extract these descriptors, and then you have to find the nearest neighbors in this database. And so that means that if we have a data set of, say, say 1,000 images, or sorry, if you have a data set of 1 million images, then you're dealing with billions of descriptors. And so we have these databases that are so large that we can't really keep them in memory. And if we want to deploy them, we have to compress them. We have to somehow get around them. So I think what these two problems have in common is that they have very large computational requirements, particularly in terms of memory. And the fact that things are so big that we cannot even keep them in memory, and we have to be clever about how we compress them such that we can still use them while they are compressed. It's a common theme that I try to approach in this talk.
Mm. It strikes me that while there's thematic commonality between these two problems, dealing with large databases and dealing with high dimensional many parameter neural networks are very different. How do you, does the connection extend to technical approaches, or is it more of this thematic connection?
It's both. It's both. So there's definitely the thematic connection where the database, let's call them databases, but or sometimes we call them data sets. They're so large, but they're also high dimensional, right? So usually these descriptors that we would extract from images, even if you go back 20 years, people were already using descriptors that had like hundreds of dimensions. Mm-hmm. So the sort of high dimensional problem was already there. Now, how do we approach now? Yeah, so I guess the talk kind of builds up upon to motivate that maybe we are facing the same problems. We can try to apply some of the same solutions. So, in particular, in this talk, we are talking about this paper a little bit more in detail. The paper is being presented in the main conference where the workshop is being held on. That's CVPR. And so here we argue that we can use this particular approach called, I guess, vector quantization, or some people might know it as product quantization. So product quantization is a very nice approach. It's not something I developed. It's an idea that originally came from a researcher that is currently at Facebook, I think. His name is Hervé Jégou. It's a paper that was published around 2011. And so it is motivated very much by this need to find nearest neighbors in high dimensional spaces very fast and with a compressed memory budget.
And is it specifically in the context of neural networks, or is it outside of that?
Yeah, so this was 2011. This was dealing with the database problem. Okay. Before neural nets were widely used. They actually have they motivate this with the computer vision setting and experiments. It's a TWiML paper, like Transactions in Pattern Analysis and Machine Intelligence. It's one of the big computer vision journals. So the data sets are from computer vision and so on. Okay. So in particular, there was this one descriptor that everyone was using back in the day called SIFT. That describes a small patch of an image. And if you have a bunch of them, you can do a lot of interesting things with the database. So the approach is actually very, very simple. And I think that's part of what makes it so nice. So we're going to have so after we extract all these descriptors, we are going to stack them on a big matrix that is going to have dimensionality D on one side. That's going to be the tiny side, and then size n, where n is the size of the database. And the thing is that D can be like 100 or something like that, but n can be 100 million or so on. The simplest way I like to explain this is you can cut these data sets into, say, 4 smaller data sets. Say if the dimensionality is 100, then each sub data set is going to have dimensionality 25. Mm-hmm. And so then we're going to run k-means on each of these little data sets, or a small representative set of that. Okay. That is going to give us 2 things. So the output of k-means is, on the one hand, the cluster centers, or we're going to call that the codebook. And then it's also going to give us an assignment for each point in that sub data set to the cluster center that is closest to it. Mm-hmm. So now what we're going to do is we're going to run these k-means with a very low k. So say k equals something like 256 is like the standard value we use. So that means that the codes are going to be numbers between 0 and 255.
Mm-hmm.
And that means that we can store them with a single byte. Now, the nice thing is that once we have these groups of codes and code books, we are going to throw away the original database. The original database that was so large we couldn't fit in memory, and these codes that are small, we can load that in RAM.
Okay.
This is of course it's going to be an approximation of the original dataset, but because you can load it in RAM, then you can do clever things with it. So the first thing is now you have extra space and something that you can manage. So you can come up with certain data structures that allow you to say do filtering, because when you have a query, even if it's compressed, even if it's very nice, easy to search, you still have hundreds of millions, and you don't want to compute hundreds of millions of distances. So you want to have some data structure that filters good candidates that are likely to be the nearest neighbor. But the other thing you can do is that you can use these codes to approximate the distance to the original vector. So when the query comes, you can also split it into 4 chunks, and then you can compute 4 tables from each little chunk to the codebook, that we computed before. Okay. So that gives us 4 tables of 255 entries each, and we can just do lookups. So if the element 2000 in the database is represented by 5 numbers called 5, 200, 120, and 255, then you can look up table 1 in index 5, table 2 in index 100, table 3 index whatever number you had, and so on.
Just to make sure I'm following you, is it fair to compare this to or make the analogy of like a hashing table or hashing algorithm, where your hashing algorithm is nearest neighbors or related to nearest neighbors?
Yeah. So hashing is also an approach that will give you, it's also used to make nearest neighbors faster. It often comes with nice theoretical guarantees. And so people like hashing because of that. Okay. One of the things that product quantization showed was that even though hashing approaches tend to have nice theoretical guarantees, in practice, they were very much outperformed by doing these quantization approaches.
Okay.
So, this was 2011. Now the literature has moved a lot on both sides.
Okay.
So, the jury, I might be wrong now. I don't follow this closely, but back in the day, that was pretty much what the evidence was saying.
Mm-hmm. And so we've got this methodology that we can use on the database side to, it sounds like, get more efficient ways to filter the data, and based on the reference to visual search as well. What's kind of the next step in your argument? How do we get closer to the application of neural network compression?
Yeah, so I think this is the less obvious point, and it's something that I was very proud of when this idea started going. Again, to be fair, like other people had experimented with vector quantization of neural nets. There are papers from 2014, 2016, and so on. But it is considerably much less explored than, so the standard approach to compress neural nets is usually scalar quantization, or things like network. There's a lot of focus on network pruning, or say low rank approximations. Vector quantization, you can count the number of papers that do that for neural networks with 1 or 2 hands.
Can you maybe talk a little bit about scalar quantization, versus vector quantization, and how those approaches work to, set us up for your application?
Yeah, so they're kind of similar. So scalar quantization is what happens when you try to look at each value in your network, or in general in any data that you have, and you're going to look at every number that you have, and you're trying to map these real floating point in practice values to a discrete subset. And so it's kind of similar to what we're doing in vector quantization. Just in scalar quantization, you're going to have one code for each scalar. In vector quantization, you're going to have one code for each vector. And of course, the question is how you define a vector, what is going to be grouped together, and so on. Mm-hmm. So theoretically, scalar quantization is going to be limited in what compression ratios it can achieve, because let's say that you're representing your numbers with a 32-bit floating point. Even in the more extreme case, you're going to reduce that to a binary value, 1 or 0. So that's going to give you a 32x compression rate.
Mm-hmm. It's pretty extreme, though.
Which is pretty good, right? It's pretty good. But when you have a network with trillions of parameters,
right,
that might still mean that you need a machine with 200 gigs of RAM or something like that.
Right. And so now you're saying if you represent a vector of 8 quantities with a single binary, then you've multiplied that out.
Yes. Or if you take like 8 values, 16 values, and so on, the bigger the vector, the more sort of bang for your buck you get in terms of compression.
Got it. Okay. And so then that is, you mentioned that there are only a handful of papers that have explored vector quantization. Any sense for why that is? Is it just hard? Did it not seem promising? Did other more promising ideas jump to the fore?
Yeah, it's a good question, actually. I am not entirely sure why that is. I think scalar quantization is very intuitive. Mm-hmm. One thing that might have happened is that when you have a scalar quantized network in particular, the way how you can use that to accelerate inference, for example, is more straightforward with current hardware. Whereas if you start mapping multiple values to a single code, then how you would accelerate that is not necessarily obvious. Mm-hmm. And so I think that might be. And so if you don't really have the memory limitation being really the main constraint, which if your network has 50 million parameters, 100 million parameters, you can probably get away with scalar quantization and still run that in decent desktops or fairly high-end phones, for example. Mm-hmm. So it might be just now that we're seeing these networks that really, really huge, that there's not going to be a way around it.
Right. And so kind of going back to the method that we discussed in the context of database, I forget, you said product
quantization.
Product quantization, yeah. So it is a fair simplification to say that in scalar and vector quantization, you're only looking at the specific quantities that you're quantizing, whereas with product quantization, now you're looking at the data that you're going to be quantizing it kind of at large.
I think that is kind of fair to say. So the thing with vector quantization is that you really have to think about what your definition of a vector is going to be. Mm-hmm. Because, for example, before we were saying we have this database that has 100 dimensions, and we were saying let's just split it into 4 groups. But the performance of vector, and if you're doing something like scalar quantization, you can take any permutation of your values. You're going to get the same compression rates. Mm-hmm. It doesn't really matter for terms of compression in which order you look at your data.
Right.
But if you're doing something like vector quantization, you might say, hey, maybe if I group the first 5 dimensions and then dimensions from 55 to 60 and then the last 10 dimensions, and I make that a single subgroup, that's going to be much easier to compress than to just take whatever dimensions happen to be together.
Mm-hmm. Yeah, I think that what I was maybe trying to get at is when you're typically applying vector quantization, you're coming up with this map. Are you also considering the entirety of your data and using that to create your quantization scheme, or is that unique to product quantization? It sounds like that may not be the
vector versus product. So I think no. So in both cases, you have to quantize everything. The gain that you get with product is that you have this freedom of having subgroups.
Okay.
Whereas if you're just doing, like, say, more, just taking your whole data set as each entry as a full vector, you wouldn't really have that.
Okay. And so how do you characterize the advantages that you get with product quantization?
So the nice thing is that because you have multiple subgroups, in the example that I was giving, say, before, you can think of it as you're expressing, for example, in that example, you're expressing your vector as 4 numbers. And those 4 numbers can take each 256 values. So in a sense, you can think of having a combinatorial sense of clusters to compress your data, because you're going to have 256 times 256 times 256 times 256 4 times. Whereas if you, so that allows you to have an implicit codebook that is very, very large, which is good for compression. Okay. Whereas if you were looking at the data as a single vector, then having a codebook of that size might not be even feasible, for example.
Okay. And then practically, how does this play out when you're using this to compress a neural network? You want to know about efficiency and accuracy and all those kinds of things, right?
Let's get into it. So the question of how we do it, I think that's a nice point. So like I was saying, the main question is, what are you going to group together? So let's say you have a matrix in your neural net that is of size 1,000 by 1,000. Mm-hmm. You can choose to split this into subsets of 4 numbers each, and then treat those of vectors, run k-means, and then get a representation that is much more compressed. So the first thing that we do is, that's what we call the paper permute, then quantize and fine tune. So the permute step is a nice observation. So neural nets have this nice property that if you have 2 adjacent layers, let's say a linear layer, some nonlinear activation, and another linear layer, some nonlinear activation, you can express the same function by having different permutations of the weights. So let's say that you choose one permutation of these 1,024 elements, and on the first layer, you're going to permute the rows according to that permutation, and then in the second layer, you're going to permute the columns. If you pass data through it, the first thing you're going to notice after the first layer is that your output is going to be permuted. And then when you process it through the second layer, because you permuted the rows, that is going to undo the permutation. Mm-hmm. The same thing is true for convolutional layers. So convolutional layers are parameterized by, say, a one-dimensional array of a lot of little three-dimensional arrays, which are the convolutional filters. Mm-hmm. The only thing that determines the order of your output, the order of the channels of the output of the first layer, is in which order you apply these filters. So that is one dimension you can permute and just alter the order of the output. And then to the layer that's downstream, you can just say, oh, you should switch the filters. You should switch the channels of your filters, and then that will undo the permutation, right?
So you're saying that you can permute, but you haven't said yet why you want to permute.
Exactly. and and that's what we've been hinting at, right? Because the key question for vector quantization to work or for product quantization to work is how am I going to form these little subgroups? If I just go and take whatever 4 numbers happen to be together because stochastic gradient descent took these values there, that might not be very easy to compress. But if I have this whole permutation, it gives me more degrees of freedom. I can search over all the permutations of the data. Well, if you search over all of them, that's going to take you a while because there's a factorial number of permutations. But you can find efficient algorithms to say stochastically look at a subset of them and then try to find one permutation that is going to make your data easier to compress. In this case, the data is going to be the weights of the network itself.
Okay.
And so then the next question is, if I give you 2 permutations, how do you know which one is better? That's the natural question. The thing is that vector quantization was a very hot topic. I'm talking about the 80s, late 80s, early 90s, because there was this big push to digitize a lot of the infrastructure that we had, to go from analog to try to make it more digital. And so the limitation that we had in doing that was that we had very little bandwidth. So we could only transmit so much binary data over, say, DSL connections or whatever we had. So there is a lot of papers, usually older papers, that deal very neatly with, say, theoretical guarantees of how you can achieve, of how to get good code books, how to get good compression rates. Yeah. So one thing people studied in particular, because back then, getting real data was really hard to get in. So there's a lot of papers on how to compress samples from a Gaussian, samples from a Laplacian, samples from other canonical, say, distributions. So for example, for a Gaussian, we know that there are well-known lower bounds, well-known upper bounds. Actually, upper bounds are harder to find. Lower bounds are easy. Okay. And so if you look at expression for this, you will see that there is some constant numbers based on how big your codebook is, how high dimensional your data is. And then there is something, there is a term, a linear term based on the determinant of the covariance of the data that you have. And intuitively, this makes a lot of sense because geometrically, the determinant of the covariance gives you a sense of how spread your data is in higher dimensions. So given 2 permutations of the data, you can compute your covariance, compute determinant, and choose whichever one has lowest determinant of covariance.
Got it. And that's right. how you create your mappings for your product quantization.
Yes, that's how you create. That's how you decide exactly which things to compress together.
Okay.
Yes. And so,
nice.
Yeah, we're pretty proud of that idea, to be honest. Yeah, we're not the first to notice that this permutation invariance exists. Like, that has been known since the 90s or so on. Probably since people started doing neural nets. I think it's kind of obvious in retrospect. And there's papers that try to use this to make optimization easier. Or, for example, there's a guy at Google Brain called Simon Kornblit. He has some papers where he's saying, okay, if you have 2 networks, you train them same data, but different initializations. How can you tell if they learn the same features? And then the question there is that the features could be the same, but they're going to be permuted differently because the initialization is different. So you have to find some sort of canonical permutation to make these things comparable. And so they do a similar search to what we were doing with a very different end goal, but exploiting the same properties.
Okay. Nice. And so then zooming out and looking broadly at the approaches that folks are taking for neural compression or compressing deep neural nets, how does this approach compare in the grand scheme of things?
Right. So in the paper, we compare against a bunch of mostly scalar quantization baselines because it's the dominant approach in the literature.
Okay.
There was a paper that we are building upon that was doing vector quantization without, without this permutation insight in particular. And when you plot this, say in the x-axis, you put the compression ratio, so 10x, 20x, 30x, and in the y-axis, you want to put how accurate your network is on whatever task you have. You see that vector approaches sort of create an envelope around all the scalar ones. And our method just kind of pushes that, I would say, by a fairly large margin, especially for high compression ratios.
In terms of implementation difficulty or efficiency, did you look at any comparisons along those dimensions?
Yeah, that is a question we get very often. So unfortunately not. So it's it takes a lot of engineering effort to make these things actually run fast. We did some preliminary experimentation where we noticed that a lot of these libraries that people often use to do inference, for example, like CUDA, cuDNN, so on, they're it's kind of hidden, but once you start poking them, they're very optimized for certain settings, and which means they're really bad for other settings. So they tend to be really good for particular batch sizes, for particular, say, sizes of data that people tend to use a lot in practice.
Okay.
But once you take them out of that range, they tend to perform not so great.
Okay.
And so, yeah, the question of how do we actually make this run fast, I think there's two ways. Either we find very talented engineers and they do it for us. But another very promising approach is, I think, looking at automatic compilers and compilers that can actually analyze the whole graph ahead of time and come up and maybe run some experiments, benchmark these things ahead of time for you, and then try to find a set of instructions that run nicely such that the actual implementation will be fast on actual hardware. That's not easy. There's a bunch of efforts. For example, Apache's TVM, I think, is very promising.
And so the promise is that there's potentially a greater engineering effort, but if you put in that effort, this is a potentially higher performance. Well, is it higher performance at a given compression level or greater compression at a given performance level, or both? I guess I'm thinking of what I'm trying to articulate is, one objective could be to, maximize your compression within, some given performance bound. Another way you might approach the problem is to, given a required compression level, what's the best performance you're going to get? Like if you can fit the model, if you have a hard limit into the model size that you need to get to, what's the best performance you can get? It's not clear to me that the same approach necessarily checks both boxes, and that's what I was trying to get at.
Yeah, so I think in practice, you can definitely set the compression rate ahead of time. And what we see is that when we do that, then in this compression to performance chart, you tend to be a little bit, so that this would be a cross section on the x-axis. So this method tends to be a little bit higher up. It's harder to say, I want this performance, then give me the smallest model I can get.
Okay.
Because, yeah, ahead of time, networks are hard to predict. You have to train them, and then you have to hope for the best. So what we do is usually we just compress for a bunch of, say, codebook sizes, and that gives us like a nice curve that tells you what the trade-offs are. And in practice, that happens to be an envelope that is Pareto optimal with respect to other approaches.
Okay, got it. And so the paper that we've been discussing thus far, Permute, Quantize, and Fine Tune, is one of a couple that you presented at or are presenting at CVPR. There's another deep multitask learning for joint localization, perception, and prediction. Can you give us a high-level overview of that one?
Yeah, of course. So first of all, I want to say I am first author on the Permute Quantize paper, but it was joint work with a bunch of other people. In particular, there's two interns, Joshan Shobrakamani and Tingwei Lu. They did a bunch of the work in this part, and shout out to them and my other colleagues at UberATG. The joint localization paper is, I am not first author there. That is the work of John Phillips, who was also an intern with us. He's finishing his undergrad right now. He's one of those interns that are doing their undergrads and they're already publishing at top venues. And
oh wow,
yes, it's more uncommon. It's getting more and more common. So that's a paper I actually like a lot too, because it's asking a question that doesn't get asked very often. So if you go to localization is given a sensor reading or a bunch of sensor readings and a map. You want to know where in the map you are. And so this is if you want to build a robot that goes around your house, or you want to build an autonomous driving car, or anytime you want to build an autonomous system, there is always going to be some sort of map, some sort of map of the world that is going to make it easier for the agent to navigate. And I guess self-driving cars are just the prime example, right? Their whole thing is that they have to navigate and that they have to do it safely. When you go, so there are a lot of papers on localization. This has been a problem that has been going on for decades. Mm-hmm. And there's a lot of approaches. There's approaches that assume that the map has certain composition. The map is high definition, low definition. Do you build it online? How much? There's memory trade-offs, computational trade-offs. It's a huge area. And the way people motivate the work in that, they usually will throw on like, oh, say you want to localize a holiday image that you took 3 years ago and you don't remember where it was taken. Or you want to, or you have an autonomous robot or a self-driving car. But the thing that they're actually optimizing for is they have this measure called localization error, which is basically how far you are from given some better sensor is telling you, you are, mm-hmm. Which makes a lot of sense, right? It's kind of the task that you're trying to solve. But when you are building, say, an autonomous system, an autonomous self-driving car, the thing you really care about is this ride comfortable and is this ride safe? I don't really care if the car thinks that I am 5 centimeters ahead of where where it actually is, or 10 or 20. As long as it's safe, it's probably fine. And so that was the question we asked, like, how can we link this localization error? How is that going to affect autonomous systems? In particular, how is that going to affect things like perception, prediction, and motion planning? By perception, I mean object detection, so detecting the cars, the pedestrians, the bikes, the motorcycles around you. If my position is, if I get that wrong, am I going to be unable or less good at detecting cars? Mm-hmm. And am I going to be worse at planning my way around them, or planning or trying to predict what they're going to do? What we notice is that if there is a small enough error, so say 5, 10, below 20 centimeters, basically your perception system, your motion planning system doesn't care. It doesn't seem to matter. Okay. And then based on that, we're saying, well, maybe we can build a localization system that runs much faster, and but it still gives us the accuracy that is good enough for our autonomous system. So we end up designing a neural net that has a branch that is dedicated to localization, and that branch can be very, very tiny. and then we can leverage a big backbone that is doing the perception and the motion and the perception and the prediction, and sort of kind of piggyback on top of those features. Try to reuse that computation that's already there, so that we can have a very, very tiny network that runs in like 2 milliseconds, 3 milliseconds,
Okay.
so that and it's still acceptable. And so we have experiments to show that this is actually possible.
Nice. In the title of the paper is Deep Multitask Learning. After you observe that you don't need your localization to be quite as accurate, then you've built a multitask network that has localization as one part of it, as opposed to localization being a standalone system. Is that correct?
Yeah, so that would be the more traditional approach, where like you will have some either some part of the stack or its own network, or often this would reflect into having its own group of engineers being a task force or a group whose task is just to improve localization. So we're kind of doing this thing jointly. And another thing we noticed besides the performance improvements is that if you are deploying this in the real world, this is, we argue, easier to deploy as well, because then your training times are much slower, so you can iterate faster, and you don't have to think of two systems at the same time. You can just have sort of one system that you, after it's trained, you can push it to the car and just get going.
Got it. Awesome. I'm curious what when you look at everything that's happening in autonomous vehicles, just your personal take, what you're excited about, where you think the field is going.
So I am really excited about Waabi. That's why I am working here. I think so. I don't know if so our co-founder, Professor Julietas, she has 20 years of experience doing AI, 10 years of experience doing self-driving, and 4 years working in industry and just in this problem. It's a lot of experience, a lot of lessons learned, and I think that having those insights and that belief that we can build something from scratch that is going to put AI center stage is not, we're not just saying that, like that's something that's backed up by a lot of experience and by seeing what limitations current approaches have.
Awesome. Well, Julieta, thanks so much for taking the time to chat with us and share a little bit about what you're up to and your recent presentations at CVPR.
Thank you so much for having me.
Thank you. Bye-bye.
Bye-bye.